When an aircraft cruises at 40,000 feet, the outside air is incredibly thin, measuring at about 1/5 of standard sea level pressure. This chart shows atmospheric pressure decreasing as altitude rises. At 1/5 of sea level pressure, human lungs simply cannot draw enough oxygen into the bloodstream. In this environment, useful consciousness lasts well under a minute. Aviation operates in an environment that is actively lethal to the passengers. Thinner air significantly reduces aerodynamic drag on the airframe. Pushing through this thin air requires less thrust, yielding the superior fuel efficiency required to make long-haul flights economically and physically viable. The atmospheric conditions that make high-altitude cruising mechanically efficient make human oxygen uptake impossible. Engineers have to artificially adapt the internal environment of the aircraft to survive the trip. Pressurization is the technological bridge that makes these efficient cruise altitudes survivable. To understand the mechanics of flight, we have to treat the fuselage as a pressure vessel defined by a metric called differential pressure. Differential pressure is the exact difference in atmospheric force between the dense internal cabin environment and the near vacuum outside. Because of this imbalance, the fuselage behaves as a rigid container, constantly fighting to hold its artificial atmosphere inside. The outward force of the internal air generates severe mechanical stress on the outer skin of the aircraft. Every decision about cabin pressurization is ultimately a structural compromise, because the stress on the metal scales linearly with that differential pressure. Since humans are evolved for a ground-level environment, it would be ideal to keep the cabin at sea-level pressure throughout the flight. But attempting to maintain a sea-level cabin while cruising at 40,000 feet introduces an immediate physics problem. This diagram compares two fuselage cross-sections. A sea-level cabin at cruise raises differential pressure by 45%. To survive this massive outward stress, the aircraft requires a significantly thicker aluminum skin and heavier internal structural frames. These structural additions carry a severe operational penalty. The extreme weight increase would drastically reduce the aircraft's payload capacity and fuel range. Building a perfect ground-level environment makes the aircraft too heavy to actually fly its intended mission. The design forces a compromise. Static strength is only one part of the engineering equation. Designers must also account for the long-term degradation of the airframe. In modern aerospace engineering, metal fatigue matters significantly more than raw static strength. This graph tracks pressure over a single flight profile, one pressurization cycle. During the climb, differential pressure peaks and the fuselage physically expands. During descent, pressure zeroes out and the airframe contracts back to its resting state. Every single flight subjects the airframe's metal to this exact repetitive cycle of expansion and contraction. Subjecting an airframe to a 45% higher differential for a sea-level cabin would accelerate this metal fatigue, severely shortening the life of the aircraft. Minimizing differential pressure is the only way to guarantee an airframe survives the tens of thousands of fatigue cycles endured over its commercial lifespan. Since structural limits demand the lowest possible internal pressure, engineers must find the absolute minimum pressure humans can safely tolerate. The vital metric used to measure this tolerance is blood oxygen saturation. This chart maps blood oxygen saturation against increasing altitude. As the altitude rises from sea level, the available oxygen steadily drops. Near 8,000 feet, blood oxygen saturation still holds steady at around 90. This regulation relies on the metric of cabin altitude, which is the equivalent standard atmospheric altitude recreated inside the pressure vessel. Under normal flight operations, 14 CFR 25.841 strictly caps this cabin altitude at 8,000 feet. While the physical aircraft flies through a lethal vacuum at 40,000 feet, the interior environment is legally locked into an 8,000-foot profile. The law explicitly enforces this 8,000-foot ceiling to mandate a non-negotiable baseline of human safety, serving as the foundational parameter for all of the aircraft's mechanical systems. Establishing the 8,000-foot limit is the theoretical baseline. Generating that artificial atmosphere is an active mechanical process. An aircraft fuselage is not a completely sealed tank holding onto a static volume of air for the duration of the flight. This schematic illustrates the true source of cabin pressure. Fresh air is continuously drawn, or bled, directly from the engine compressors. Because this highly compressed engine air is incredibly hot, it must pass through cooling and conditioning packs before it enters the main cabin space. The engines operate as continuous high-volume pumps, providing a limitless supply of raw, pressurized air to the vessel. This conditioned air moves in a continuous, steady flow dynamically through the passenger cabin. Cabin pressure is set by how fast air leaves the vessel, rather than by how fast it enters. This exhaust rate is regulated by a specific piece of hardware located at the extreme rear of the fuselage, the outflow valve. The outflow valve constantly modulates, opening and closing to actively control the rate at which air escapes the aircraft. By restricting this exhaust, the outflow valve forces the incoming engine air to compress exactly to the equivalent pressure of 8,000 feet. 8,000 feet is a structural limit and a physiological limit meeting in the middle.